the agenda of today's webinar. I'll give you a general overview of ASAP, so the main feature, with a very, very brief demo. And then I will leave the floor to Irina, which will introduce you to the nanotransport feature of ASAP with a very detailed demo. This webinar is being recorded, so for you to know. I also like to mention that for this first webinar, we decided not to include any Q&A section. However, as I mentioned in the previous slide, please contact us by email if you have any questions. So let's move on. So ASAP stands for Atomistic Simulation Advanced Platform. And it is our software, and it has a catchy graphical user interface, as you will see later. It's easy to install and run on Mac, Linux, and Windows. And it features powerful servers such as Siesta, Quantum Espresso, and Transiesta. Okay, this is ASAP main screen. This is a screenshot. As you can see here from the main windows, the user can see all the project and their status. As you see from these slides and the following, our goal is to make a powerful yet intuitive interface. So we put our effort in creating a tool that any kind of user, not only expert, also beginner, can use with relatively little effort. And we wanted to basically decrease the learning barrier to make possible using ASAP from the moment in which the software is launched for the first time. So in the screenshot here, you can see how you have a project for each line, and there is a series of buttons from left to right that make the necessary step to be taken to perform the simulation. So we have from the left the definition of the basically the structure, okay, for your project. Then you have one first button to define the project type, the following the parameters for that specific project that you selected, the calculator setup. So as I mentioned before, the calculators are Siesta, Quantum Espresso, and Transiesta. Then you have a button specifically designed to launch the calculation. This can be done locally or on a remote server. So yeah, it's possible. Both options are available. And then you have another button here, analysis, which is active when the calculation is completed, and from which you can basically explore and view the results of your simulation. We also have a button here on the far right there's a note button, so you can write some notes there and to remember what you've been doing in the project. So as I mentioned, the first step is to define the atomic structure. This is how any ASAP project starts. This can be done, okay, by creating a structure from scratch. So using these shortcuts that are available in ASAP, you can load a molecule from our database. You can build a surface, a periodic structure, a bulk, nanotubes, nanoribbon, and clusters. It is anyway possible to import pre-existing structure that can be downloaded from the web or coming from other calculations, and from a wide variety of file formats. So we support XYZ, CIF, CSS output file, PDB, and many others. Another interesting feature is that it's possible to merge two systems once the projects are created. This is particularly useful, for example, when someone wants to create a system which, for example, is a molecule on a surface, or as Irina will show you later, when you want to perform some transport calculation in which you need to build the device. And you do this basically by putting together a structure initialized in existing project. Here is just a slide with a screenshot of the different widgets to create the different kind of structure in ASAP. So you have molecule, bulk, cluster, surface, nanoribbon, and nanotube. The next step, once the project is created, so the structure has been initialized, is to decide the kind of project that you want to basically to simulate, the kind of simulation that you want to simulate. Here you can see an example of the parameter widget for the geometry optimization project. However, many other projects are available, and we can divide them in general. So we have projects for general application and electronics, mechanical properties, chemistry, material science and photonics, surfaces, and electronic transport, as you will see in the second part of the webinar. After choosing the project type, the users select the calculator. So the calculator is a graphical user interface, and it is designed to assist the user in selecting the computational engine and preparing properly the input file. ASAP currently support EMT, which is an effective medium theory calculator. Is used mainly for testing and demonstration. Siesta, Siesta 4.0, Siesta 4.1, and soon, in the next release, Siesta 5. Siesta is a linear combination of atomic orbital DFT code with highly tunable performance, and it can treat periodic system, finite system, open system, basically any kind of system. Then we have Quantum Espresso. It's always a DFT code, but it's a plane wave code in this case. And as Siesta, it can treat any kind of system, so bulk, surfaces, molecules. Finally, we have Transesta code. We support Transesta code. Now, Transesta code is basically implementation of non-equilibrium electronic transport in Transesta. But Irina will explain all this in the second part of the webinar. Once all the setup for the calculation has been chosen, the next step is to run the calculation. So this is the widget to run the calculation. This, as I mentioned before, can be done locally or on a remote server. The user can always monitor the status of the simulation and inspect directly the output file if this is necessary. Once the calculation is completed, as can be seen from this slide, you have this completed flag here. So the user can view the results in the analysis widget. And this brings me to the next slide. Here, obviously, the analysis depends on the kind of calculation and project that the user is choosing. So we cannot show all of them. Here we can just show 3 screenshots. So this is an example of the analysis widget for analyzing the mass structure of a periodic system and the density of states. In the center, we have a plot of the density of vibration modes. This is a vibration project to basically analyze how the molecule or system, well, it's a finite system, is vibrating. And here on the right, we have an energy profile, which has been extracted from an NEB calculation, which is basically, if you don't know about it, is a project that is very useful to extract information about chemical reactions. So in this case, for example, you might imagine that you have a final state, an initial state of a chemical reaction, and you want to explore how the system goes from one state to another.